everyone, and welcome to our lesson on modeling with quadratic functions. Remember, quadratic functions are our parabolas. There are lots of situations in the real world that follow a parabolic path, so they can be modeled with these equations, and it's really pretty neat. Lots of sports situations, anything where you're throwing a ball up in the air and it's landing at a certain point in time, anything like that. So we're going to take a look at a situation like that and answer a lot of things about what's happening just based on our graph of that quadratic. Alright, so we're going to take a look at an example of someone who's kicking a soccer ball on the field to score a goal. And if you can picture that in your mind, the person's going to come up and kick the ball from the ground. It's going to travel up in the air, and then it's going to have sort of a curved path and then eventually land back down on the ground. We have a function that's representing that down here, negative 2x squared plus 12x. That's the equation of a parabola that is opening downward, so it's modeling our situation. So we're given that equation, and we're going to be given the graph, and we're going to be asked a couple of different things about what's happening. Alright, so you can either look at your graph visually, and sometimes you may have to estimate, because when you get into the real world situations, the values may not always occur on an actual whole number or integer. They may be off the marks a little bit, but we can always estimate on those. So we want to know a couple of special points here. We want to know where the path is crossing the x-axis, because that's going to be our zero line where the ball is starting and stopping. And then we want to find the vertex, because that's where something's changing. That's where it's changing direction, it's reached its maximum height, and it's traveling back down. So we can do that from the graph, or if we're given an equation, we can solve it algebraically that way too. So let's say that we're asked about those x-intercepts and what they represent. So we have a couple of them here. We can see where the graph crosses the x-axis. And let's say that we can see that visually, and we confirmed with algebra that it is crossing at 0, 0, and 0, and 6, 0. So think about what that means for the person kicking that soccer ball, is that on the x-axis we have our time in seconds. So at 0 seconds, that ball has no height yet. And then when we travel out to 6 seconds, again, we're back down to 0 height. So that's what that is representing there. All right, let's say that we're asked about at which point in time the ball is a certain height in the air. Well, we know that our y-axis here is representing our height of the ball. So let's say we, for instance, would like to know at what interval of time the ball is above 16 feet. We're just going to find that on our y-axis. So it looks like, according to our grid marks here, there's our height of 16 level. And we're just going to match that to the x-axis to be able to answer that question. I'm going to travel down here and find where that occurs. Looks like the interval of time between 2 seconds and 4 is where that's happening. So we would say between 2 and 4 seconds. We would just do that for any height amount that we were asked about. Alright, what if we need to know something about the vertex? What if we're asked, what is special about that point? Well, we know, if we think about our situation, that this is the highest height that the ball ever reaches. So what's happening there is it's coming to, it's slowing down, it's reaching its maximum height, and then it's going to fall back down to the ground. So what it means is at 3 seconds is when that maximum height of 18 feet occurs. All right, and we can answer any number of things based on that graph. We may be asked about what interval of time it's increasing in height, what interval of time it's decreasing. We would just go match our y levels to our x-axis to be able to answer those. So very useful things to be able to look at the graph and our equation to answer things about the real world models. One thing I wanted to let us look at is when we start dealing with these real world topics, what would be a reasonable domain, and maybe we might be asked about the range also of our function. Well, domain is the x values that our function occurs on. So if we think about what that's actually representing, we're back on our picture now. Our x was our time. So normally a quadratic function is going to have a domain of all real numbers. It's going to travel on forever and ever in both directions. But in our case here, we won't be dealing with a negative time. That just wouldn't make sense. So a reasonable domain for us is where our ball starts and stops. It's 0 seconds to 6 seconds. We would never travel into negative seconds there. And same thing when we're describing range depending on the situation. And this concludes our lesson on modeling with quadratic functions.